Welcome back to the ARSET training, Sea Level Change Tools for Planning and Decision Support. My name is Sean McCartney, an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the second and final part of this two-part training on sea level change. The following slides provide an overview of the two-part webinar series. Earth's seas are rising because of a changing climate, and this rate is projected to increase over the next century. Due to the warming atmosphere and ocean, ice sheets and mountain glaciers are melting, resulting in the addition of fresh water into the ocean. Ocean water expands as it absorbs trapped heat, causing sea levels to rise. Data on this increase in the rate of global sea level rise is critical to planners understanding the trajectory of future sea level rise. The learning objectives are as follows. By the end of this two-part training, participants will be able to identify underlying Earth processes contributing to relative sea level change at global and regional scales, recognize remote sensing and model data used for assessing sea level change on a regional to global scale, describe how coastal communities and infrastructure can be impacted by flooding caused by sea level change, demonstrate how to assess the processes contributing to past and future sea level change with the Sea Level Explorer tool at global and regional scales. Demonstrate how to access future projections of relative sea level change under different emission scenarios with the IPCC AR6 projection tool. And visualize oceanic and groundwater flooding maps with the Pacific Islands flooding tool. The prerequisite for this training is our Fundamentals of Remote Sensing course. We recently relaunched a new interactive online self-paced Fundamentals of Remote Sensing training on the ARSET learning management system, and we hope you will work through it at your own pace and share it with your interested colleagues. Over these 2 weeks, from June 10th to June 17th, there have been two 1.5-hour sessions, which include presentations, demonstrations, and question and answer sessions. All materials and recordings from each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours on the ARSET training webpage. Homework opens on June 17th and will be due on July 1st. You will be able to access the homework from the training page on June 17th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment by the given due date. Part 2 of the training is focused on assessment tools for sea level change. By the end of Part 2, participants will be able to demonstrate how to access future projections of relative sea level change under different emission scenarios with the IPCC AR6 projection tool, and visualize oceanic and groundwater flooding maps with the Pacific Islands flooding tool. Please put your questions in the questions box, and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the Q&A session after the webinar. The remainder of the questions will be answered in the Q&A document, which will be posted to the training website about 1 week after today's training. It is now my pleasure to introduce the guest trainers for today's webinar, Dr. Robert Kopp, Dr. Phil Thompson, and Dr. Denis Felikson. Dr. Kopp is a climate scientist who serves at Rutgers University as a distinguished professor in the Department of Earth and Planetary Sciences. Professor Kopp's research focuses on past and future sea level change, the interactions between physical climate change and the economy, the use of climate risk information to inform decision-making, and the role of higher education in supporting societal climate risk management. He directs the Megalopolitan Coastal Transformation Hub, a Rutgers-led consortium that advances coastal climate adaptation and the scientific understanding of natural and human coastal climate dynamics. He is also co-lead for engagement and applications for the NASA Sea Level Change team. He was a lead author of the Intergovernmental Panel on Climate Change's 6th Assessment Report, and is a fellow of the American Geophysical Union and the American Association for the Advancement of Science, and a 2024 Guggenheim Fellow. Dr. Thompson is an associate professor in the Department of Oceanography at the University of Hawaii, Manoa, and director of the University of Hawaii Sea Level Center. He is an oceanographer interested in turning sea level data and projections into actionable information for coastal communities. His research group operates at every stage of the process, from data collection and quality control to research and analysis to data visualization and product development. He leads projects funded by NASA, NOAA, USGS, and others to not only understand how and why our coastlines are changing, but to distill these findings into data-driven products that support decision-making. Dr. Felikson is the Deputy Project Scientist of NASA's ICESat-2 mission at NASA Goddard Space Flight Center, as well as the lead of the Integration Working Group on NASA's Sea Level Change team, and co-lead of the Greenland Ocean Forcing Focus Group for the Ice Sheet Model Intercomparison Project for CMIP-7. His research interests focus on combining observations and models of Earth's ice sheets to understand the processes that drive their change and to improve projections of sea level rise. Bob, over to you.
Thank you, Sean. My name is Bob Kopp. I am a distinguished professor of Earth and Planetary Sciences at Rutgers University in New Jersey. I'm also one of the co-leads of the NASA Sea Level Change team. And of relevance for this presentation, I was one of the lead authors on the IPCC 6th Assessment Report, from which I'll be using some information. So to project future sea level changes, we need to integrate information about different processes that come from different sources. There is no single Earth system model, for example, that recognizes that models all of the processes contributing to sea level change. So we need to be able to model and project a set of processes that are associated with oceans and atmosphere and how they interact. Processes like the expansion of the ocean as it takes up heat and the shift in the height of the ocean as fresh water moves around within it. The processes like changes in ocean circulation, processes like ocean-atmosphere interaction driven by wind. All of those processes are ones that can be modeled reasonably well by global climate models. But we also have to model movement of mass from the land into the ocean. So the largest contributor there is the melting of ice on land in mountain glaciers and the loss of ice from the polar ice sheets in Greenland and Antarctica. And then there's also a contribution there from the change in the amount of water stored on land, both stored naturally through fluctuations in things like the size of inland lakes, but also artificially through things like dam construction, which holds back water that might otherwise flow into the ocean, and groundwater pumping, which removes water that was stored in the ground, allowing some portion of it to flow into the ocean. So all of those factors then have an additional layer of complication layered on top of them when you look at a local scale. Because not only do you have processes like ocean circulation and winds moving around water at the surface of the ocean, you also have changes to the Earth's gravitational field and the Earth's rotation that happen when you move big masses like those masses of ice around at the Earth's surface. So for example, if we lose mass from Greenland, because you're affecting the ice sheet's gravitational field, you actually have a sea level fall near Greenland, even as global average sea level rises. And then on top of that, you also have to consider the effect of vertical land motion. For instance, subsidence in areas that are on the edges of former ice sheets or that are on deltaic sediments subject to compression, or uplift in areas that are tectonic, some areas that are tectonically active. Now, there's another a set of information you also need to think about. When we talk about sea level projections, how we think about uncertainty is also core to that, because we need to quantify those uncertainties to the extent that we can in order to communicate and manage the risk of sea level change appropriately. So it's common in this literature to draw upon the framework established by the IPCC, the Intergovernmental Panel on Climate Change. And the IPCC sort of has two separate scales for characterizing uncertainty. One is a scale of confidence, the other a scale of likelihood. The confidence scale measures the amount of evidence and the degree of agreement among evidence for various findings. For instance, if we have a broad range of evidence that all agrees, we would say a finding has high confidence and be over here in this portion of the figure. If, on the other hand, we are looking at a topic on the frontier of scientific understanding, we are often in a situation where there is limited evidence and a low-level agreement among those pieces of evidence. So we would call that low confidence. And that's important when we think about sea level rise, because there are certain processes which we can model with medium or high confidence. Things like some of those ocean dynamic changes or changes in glaciers. But there are also critical processes involving ice sheets and the potential instability of ice sheets that are on the frontier of scientific understanding and in which we therefore have low confidence, but still could be driving some of the biggest risks and therefore cannot simply be neglected because they are low confidence. Where there is medium or high confidence, the IPCC then goes on to assess likelihood. How likely, how probable are different outcomes. So this is what this chart on the right shows. And in particular, I'm going to focus on the term likely, which we often use in communicating the IPCC sea level projections, where the likely range is a range of projections in which essentially all the approaches used to produce those projections agree there's at least a 66% chance, at least a 2 in 3 chance that the correct value lies within their range. Now, importantly, again, we only assess likelihood in areas of medium or high confidence. So when I tell you a likely range for sea level based on the IPCC, it's important to bear in mind that's the likely contribution from that set of processes in which there's at least medium confidence. And it doesn't include potential additional contributions from frontier areas of science in which there is low confidence. Related to this is also the concept of deep uncertainty. It's another concept used by the IPCC and is closely related to low confidence. Deep uncertainty occurs when analysts do not know, or the parties to a decision cannot agree upon, the appropriate models to describe the interactions among a system's variables, or the probability distributions to represent uncertainty about key variables and parameters in the model. And this arises at several places in sea level projections, most notably in describing future emissions and in describing some of these potential ice sheet instability processes. Now, in the IPCC, we used a framework which is developed with support from the NASA Sea Level Change team called FACS, the Framework for Assessing Changes to Sea Level. And this is a framework for drawing together models representing different portions of that diagram I showed you earlier to produce integrated projections of global mean sea level change and local relative sea level change. And so briefly, I'm just going to walk you through this flowchart. So we start over here with emissions. Emissions drive changes in climate, which are reflected in variables that we emulate, such as global mean temperature or the total amount of heat stored in the ocean. These variables then drive a set of processes, one of which is called stereodynamic sea level. And those are those several processes I told you before are reasonably well represented in global climate models. Process like changes in the density of the ocean it takes up heat and it has salt moves around. Processes like ocean circulation changes, processes like ocean atmosphere interactions. And then those sets of processes that involves ice on land, modeling the behavior of ice sheets, modeling the behavior of mountain glaciers. And then there's another set of processes, the land water storage, that are not driven directly by climate, but are driven by population changes. So these are the human-caused drivers of changes in land water storage, like dam construction and groundwater pumping. The ice sheet, glaciers, and land water storage projections are then combined with those gravitational, rotational, and deformational effects that produce that phenomena I mentioned before, where, say, near a melting ice sheet, you see a decrease in sea level, even as you see a global increase, so that you can then translate those as a contribution into relative sea level change. That's combined with those stereodynamic sea level projections, and is combined with projections of other drivers of changes in the height of the land, vertical land motion. So to walk you through a few elements of this in greater detail, I want to start with emissions. Now, a key driver of the range of possible future sea level change is the range of possible human emissions. So we're showing here on this plot global emissions of carbon dioxide from 1960 current up to about 1992. And if you think back to the 1980s, since the start of the Industrial Revolution, humans had emitted about 600 billion metric tons of carbon dioxide from fossil fuels. And together with deforestation emissions and other greenhouse gases, this had raised global average temperature by about 0.4 of a degree Celsius above their pre-industrial levels. If we had had a policy change, and starting in 1992, when international climate talks first began, we had gotten carbon dioxide emissions on a downward trajectory. We could have had about 90 years to get global emissions to zero and still have a good chance at stabilizing the climate at well below 2 degrees Celsius, which is one of the international goals agreed to in the 2015 Paris Agreement. This trajectory shown here would likely have led to about 1.8 degrees C of warming by the end of the century. But we didn't get on that future, and instead carbon dioxide emissions continued climbing. They are now in excess of 40 billion tons of fossil carbon dioxide emitted into the air every year. And as a consequence, the planet's temperature has increased by almost an additional degree Celsius since the mid-1980s, and we're feeling the consequences of that. Now, let's talk about another future. What a couple decades ago we might have called business as usual. If over the 2010s, emissions had continued growing at the same pace as they did in the prior decade, we would have been on something like the trajectory shown here in red, on track for about 4 degrees Celsius of warming by the end of the century. And this red curve here is one that is called in the jargon of the IPCC and the climate modeling community SSP 3.7. But this isn't the trajectory we were on in the 2010s either. Emission growth has been slowing as a result of the combination of policy and market-driven retirement of coal and the growth of renewable energy. So now, it is still possible to achieve the Paris Agreement goal of limiting warming to 2 degrees C, but instead of getting to zero in 90 years, we'd have to do it by about 2050. Alternatively, as shown in the pathway here, which is known in the jargon of the climate modeling community as SSP1 2.6, we could take a little longer and hope that we have the right technology and land use policies in place by the end of the century so that humans are actually actively sucking carbon dioxide out of the atmosphere. And here's a third future. This is the future sort of closest to where global climate policy is taking us, which puts us on track for almost 3 degrees Celsius of warming by the end of the century. This is the future called SSP2 4.5 in the jargon of the climate modeling community. So we feed emissions trajectories like those into facts, and then that gets fed through to this variety of models shown here. Now, I want to highlight the ice sheets here because of that deep uncertainty I mentioned earlier. Different ice sheet modeling approaches yield different sea level distributions. And that's reflected in these probability charts here. So on the left, we're looking at 4 different ways of modeling global mean sea level in that low emission scenario, SSP1 2.6, and on the right, in a very high emission scenario, SSP5 8.5. And each of these probability distributions, these bell curves or skewed bell curves, represent a different way of modeling the ice sheet contribution to sea level. So 2 of these, the blue curves labeled as ISMIP6 and LARMIP, are projections driven by a suite of ice sheet models and are judged to capture processes in which there's at least medium agreement and evidence, and thus medium confidence. But as I mentioned, those low confidence processes are also important for risk management. And so we also consider 2 additional approaches labeled with Mickey and SCJ that provide limited evidence for processes in which there's low confidence. And you notice that that doesn't make a huge difference under the low emission scenario on the left, but can lead to quite different distributions on the right. And finally, I want to talk about integrated global mean sea level and relative sea level projections, the output of FACS experiments. And here I'm going to switch over to the IPCC logos because this is all results representing what we said in the IPCC 6th assessment report. So we know that sea level is going to continue to rise for many centuries to come, creating an escalating hazard for coastal communities. And that's reflected in this chart on the left, which shows in black historical sea level global mean sea level rise since 1950, and then a suite of different curves reflecting different emissions trajectories here, and an indicative curve reflecting the potential contributions at quite a high end, at the 83rd percentile, with very high emissions from these low confidence processes. So what emerges from this is that through the middle of the century, sea level projections exhibit limited sensitivity to plausible changes in greenhouse gas emissions. Relative to the 1995 to 2014 average, the likely global mean sea level rise by 2050 is about 20 to 30 centimeters under a high emission scenario and about 15 to 25 centimeters under a low emission scenarios. And again, recall that likely means at least a 2 in 3 chance that the real value will be in that range. As a consequence, extreme sea levels that occurred once per century in the recent past will occur about 20 to 30 times more frequently by 2050. Beyond 2050, sea level projections are increasingly sensitive to the difference between emissions pathways. So the likely global mean sea level rise by 2100 is about 60 to 90 centimeters under a high emission scenario, SSP 3.7.0, and about 30 to 60 centimeters under a low emission scenario, SSP 1.2.6, with those differences growing to about 1 to 2 meters by 2150 versus to about 50 to 100 centimeters by 2150 under the low emission scenario. And again, likely ranges means these are only considering those processes in which there's at least medium or high confidence, not considering low confidence processes. But we can also say that the more we limit our emissions, the lower the chance we trigger these low confidence instabilities in the polar ice sheets that could substantially increase sea level rise. Higher global mean sea level above the likely range before 2100 could be caused by earlier than projected disintegration of marine ice shelves, allowing the abrupt, widespread onset of marine ice sheet instability, which is where the ice sheet essentially gets eroded from underneath by the ocean, or marine ice cliff instability, both of these in Antarctica, where marine ice cliff instability is essentially where you lose the floating ice, the ice shelves, and then you end up with cliffs that collapse under their own gravitational weight. It can also be caused by faster than projected changes in the surface melt and runoff from the Greenland ice sheet. And the sixth assessment report concluded that global mean sea level rise well above the likely range, approaching 2 meters by 2100 and 5 meters by 2150 under a very high greenhouse gas emission scenario, cannot be ruled out. Although this wasn't available in time for this sixth assessment report, work that my groups conducted after the sixth assessment report suggests that for the intermediate emission scenario that most closely resembles current policy, we would say that global mean sea level rise approaching 1.5 meters by 2100 and 3.6 meters by 2150 cannot be ruled out. Now, what I've showed you so far is all about global mean sea level. But sea level rise varies locally, as we talked about before, which is why NASA and the IPCC partnered to create the sea level projection tool, which you can access at sealevel.nasa.gov/IPCC. And this tool allows you to go into locations all around the world, either grid cells shown on this map or the tide gauges indicated by the dot, and produce figures for that location that look like those shown in the IPCC report for global mean sea level. For instance, we can go in to Washington, D.C. and produce a plot sign here and an associated table, which will tell us that the likely sea level rise in Washington, D.C. by 2100 is about 80 to 120 centimeters under a high emission scenario and about 50 to 90 centimeters under a low emission scenario compared to those global numbers. And that sea level rise exceeding 1.7 meter at the 83rd percentile under very high emissions cannot be ruled out. There's also another way of looking at these projections, which is rather than looking at uncertainty in how high sea level goes at a particular point in time, look at uncertainty in when sea level exceeds a given limit. And this tells us that the more we limit our emissions, the more time we have to adapt. So in the IPCC report, we have figures like this. So this is for half a meter of global mean sea level rise. These are different emission scenarios. The dark bars show the range in which that half meter will likely be exceeded, considering only medium confidence and high confidence processes. And the light bar for these two scenarios, SSP1 2.6 and SSP5 8.5, illustrates the potential contribution of low confidence processes. So considering only medium confidence processes, global mean sea level rise is likely to exceed half a meter between about 2080 and 2170 under low emissions, SSP1 2.6, and between about 2070 and 2090 under very high emissions, and is likely to exceed 1 meter between about 2150 and sometime after 2300 under low emissions, and between about 2100 and 2150 under very high emissions. And when we consider also projections, processes in whose projections there's low confidence, we see these numbers creep up even higher. At the 83rd percentile under very high emissions, we could be looking at 1 meter being exceeded by about 2080 and about 2 meters being exceeded by about 2110. And you can go into the tool and pull up these same plots for any locations on the map. So this is showing you for Washington, D.C., the timing of exceedance of 0.6 meters, 2 feet on the left, and 1 meter, 3.3 feet on the right. So for example, under the intermediate emission scenario, SSP 2.545 at Washington, D.C., considering only medium and high confidence processes, 0.6 of a meter of sea level rise will likely be exceeded by about 2060 to 2100, and 1 meter between about 2090 and 2170. And I'll leave you with these 3 resources. The first is a projection tool, the second, the 6 assessment report itself, and the third is a paper we've written that provides you greater detail in topics like uncertainty and ambiguity in sea level rise that can help interpret in greater detail some of the reports, some of the projections produced by the IPCC. Now I'm going to do a brief demonstration of the NASA IPCC sea level projection tool. So let's start. So over here on the left, you'll see some controls. You can look at the projections either organized by scenario, like we were talking about in the talk, or by warming levels at the end of the century. You can look at this map here. This is currently showing total sea level. We can change it to look at the contributions from a variety of different processes or rate of sea level rise. You can look at different decades. This is 2100. And the map can be used to look at different scenarios. Most users of this are going to want to dive into a particular location, but just briefly, if we go to view global projection, we can look at some of the same sorts of results that you see in the IPCC report. So just notice here, we can also switch between scenario and warming level projections and between metric and American units. So this plot here is showing you projections in this case for SSP 245. You can turn on different scenarios here. All of these on the left are only considering medium confidence processes, but we can also, for instance, turn on the SSP 585 low confidence projection. Scroll down a little further, and you can see that timing of sea level rise milestones. So these are for those 5 emission scenarios. So SSP1 1.9, which is about a 1.5 degree scenario. SSP1 2.6, which we focused on in the talk as a low emission scenario. SSP 245, SSP 37, that was a high emissions in the talk, and then SSP 585. And all of these bars are only considering medium or high confidence processes. These two for SSP 1 2.6 and SSP 5 8.5 consider the additional contribution of low confidence processes. The thick bars are all 17th to 83rd percentile, so that's likely ranges down here, or we don't call them likely ranges when we include low confidence processes, but that's the 17th to 83rd, and then this is 5th to 95th percentile. This is showing you exceedance of half a meter, but we could, for instance, look at 1 meter or some other level. And this is showing you the sea level projections under the 5 emission scenarios and the 2 low confidence scenarios, in this case for 2100, but we can change the year, showing total amounts down here. So this is the median value and then the full likely range. And then this is showing you how these totals come from thermal expansion, glaciers, Greenland, Antarctica, and land water storage. And this plot down here is similar, but instead of looking at sea level, it is looking at the rates of sea level change. So this is rate 2040 to 2060, so 4.1 millimeter per year median rate. Here 2080 to 2100, 4.2 millimeters per year. And it's also showing you the totals for a set of different time points, 2030, 2050, 2090, 2100, and 2150. Now, again, this is all global. I pulled up on the left here under View Global Projections, but we can scroll around the map, we can zoom in, or we can search for different locations. So let's go to Wilmington, North Carolina, and we see these same results. Here we have our chart of the different projections, which we can turn on. We have our timing of different milestones. So here's 0.9 meters or 3 feet, when that will be exceeded under different emission scenarios and when considering low confidence processes in Wilmington. This is that table, in this case for 2100, but we can change that to say 2050, of the contributions of different terms to sea level, total sea level rise in Wilmington, the stereodynamic sea level. So now not just global mean thermal expansion, but also considering changes in ocean circulation and winds, glaciers, Greenland, Antarctica, land water storage, all of these now taking into account the gravitational, rotational, and deformational effects, and then vertical land motion. Here's the summary for those 5 time periods, and then the rates of change for 2040 to 2060 and 2080 to 2100. So with that, I think you have enough knowledge. Now you can go back, you can play with the tool, you can pull up your favorite tide gauge. So we can pull up a different tide gauge here. This is Oregon Inlet Marina. We could go to full projection, or you can go to a grid cell and do the same thing. And so I hope you find this tool useful in helping access local sea level rise projections based on the analysis done in the IPCC 6th Assessment Report. Now I'm going to pass it to Phil Thompson to present the flooding analysis tool.
Okay, thank you, Bob. Appreciate that introduction to the sea level rise projections. So now what I'm going to do is take the baton from you, and I'm going to switch over here and talk about the Pacific Islands Flooding Analysis Tool, which is taking those sea level rise projections that Bob just talked about and then applying them to figure out how the changes in flooding frequency will evolve going forward over the rest of the century based on those projections. And my name is Phil Thompson. Sorry, I forgot to mention that. I'm Phil Thompson from the University of Hawaii, and I've been on the NASA Sea Level Change team for many years now, going back to its inception. Okay, so Bob already talked about sea level rise itself, and of course, what we care about the most from an impacts perspective, what do we care about? Of course, the average water level is going up. That's not great. That means that means that average high tide is also going up. Obviously, that's going to start to impact things. But what we really care about is where the high tide, the highest tides of the year, not the average high tide, but the highest tides of the year, how those start to begin to creep up over flooding thresholds. And here's just a couple of examples here on the right side from Honolulu, where I live and work. You can see that these are flooding events in the streets, in parking lots. This is not part of a big storm or hurricane or anything like that. This is just a higher than normal tide backing water up into our storm drainage systems and creeping out into our public spaces or into our coastal infrastructure. And so these are the types of things. They're not happening very often yet, but they are starting to occur occasionally. And so we're starting to think about, how is this going to begin to look in the future as these events become more and more frequent? So we care about those high tides above flooding thresholds. And so what we want to do in this tool that I'm going to describe for you is we want to focus on the number of days per year that high tide or the highest water level of a day will exceed some threshold. Now, when we talk about numbers of days per year, there are various opinions about how you label these types of frequencies of flooding, but something around 25 days per year is generally considered chronic from the literature, the scientific literature. And then once you get out to 50 to 100 days of flooding per year, that land is essentially unusable at that point. So you really kind of care about something before those very large numbers of days per year. So when we talk about NASA's effort here, and they've invested a lot in sea level rise through the NASA Sea Level Change team, and also in developing tools like the one I'm going to show you here. And we have a couple of ones that I've developed in my group at the University of Hawaii for NASA. One of them, the one I'm going to show you today, is focused on the Pacific Islands, and that's based on the IPCC projections that Bob already told you about. And we're going to focus on that one today because it has a mapping component. It's our sort of latest effort in this area, and we've introduced a mapping component to it that's really helpful. There's another one that is focused on U.S. coastlines only, and it uses the U.S. sea level rise scenarios, which we haven't talked about here. So we're not going to talk about that one today because eventually we're going to combine these two, and we're going to focus more on the IPCC sea level rise projections anyway. So just keep that in mind. Right now, this is only for the Pacific Islands, but we do have plans over the next couple of years to expand it out globally, including to the US. Okay, so when we talk about flooding, there are two types of flooding exposure, and it's important to distinguish between them. One is oceanic flooding. This is the kind of flooding that you would typically think about, where the ocean is rising and then the ocean starts to creep into the land area and the infrastructure, the coastal infrastructure. So this is ocean water flowing directly onto the land at high tide. But of course, then we also have a different kind of flooding, which is groundwater flooding. And if you're not sort of thinking about sea level rise and climate change, or living in a Pacific island or a coastal community, this is one you may not think about right away. And this is flooding that occurs not from ocean water coming onto the land, but from groundwater rising up from below. And on the right-hand side here of the screen, you can see this sort of darker shade of blue here. This is where the groundwater would be before sea level rise. And then after sea level rises, it actually exerts a pressure on that groundwater reservoir, and it causes the groundwater to rise up. And as the groundwater rises up, you can see it kind of gets out into some of these low-lying areas on the land. And so that's the kind of flooding that is maybe less obvious, and also potentially more difficult to plan for, because you can't build a seawall, right? You can't build a seawall to keep the water from rising out below your feet. Okay, so in our flooding analysis tool with the Pacific Islands, we include both. We talk about we delineate areas that are exposed to groundwater flooding and also oceanic flooding. The groundwater flooding is harder to estimate because if you want to do that really well, you have to know a lot about where the groundwater already is, and how it relates to the ocean. So what we do is we say that there are areas that are vulnerable to groundwater flooding, where the inland area is less than where the high tide area will be. So that's kind of how we delineate this. Just keep in mind that that's a little more uncertain, but it is important to know areas that are vulnerable to it so you can begin to think about, or even do a more detailed study if it really looks like it's going to be a problem. Now, one caveat in this tool that I think it's important to note is that the tool does not include the impact of waves. That is also something that needs specific local modeling to try to understand. So in that sense, what's in this tool is sort of a lower bound on the impacts you can expect. And this is mostly applicable in areas like in ports and harbors and things like that, where you don't have a lot of large wave activity. And then you can think of it as kind of a lower bound on the impacts for places where there are waves, like on beaches and places like that. Okay, so let's look a little bit about what the tool about how the tool works, and then at the end, I will, after I sort of describe how it works, I will jump over and show you the tool itself, and we'll kind of do the same thing I'm going to walk you through here, but live in the tool, just so you can kind of see how it works. And I think that will be helpful. Okay, so when you land on the tool, you'll see a map. And then you'll see some dots where we have done, these represent the locations of islands where we have done the analysis. This is where there is local sea level data for us to use for this. And then we also have them separated out with open circles where we don't have the flood mapping yet. We're working on filling in all these circles. This is a work in progress. And the closed circle, the filled circle here, that's where we do have the mapping available. And that requires satellite derived estimates of the land surface and how it varies vertically from place to place. So that's why in some places we've done that analysis and other places we haven't. Okay, and I've already mentioned that we will be expanding this out globally. I mentioned that earlier. So eventually these open circles will get filled, and then we're going to expand to many more locations around the globe. So this is kind of what you'll see when you first land. So you got to choose a location. In this example, I've chosen Tuvalu, which is a place that is very vulnerable to sea level rise. And also it's a place that NASA recently produced a technical report about in using some of these same approaches. And so I wanted to focus on that one here. And if you want to read that report, we can find that link for you and share it with you. So the first thing you have to do, though, when you think about assessing the impacts of sea level rise in terms of flooding frequency, you need to know at what level you're concerned about. So you need to choose a flooding threshold. And it's important to note that a flooding threshold for one place may be different than a flooding threshold elsewhere. So you want to kind of choose a threshold. If you're worried about an entire community or an island, then you want to choose a threshold that's sort of broadly relevant if you're looking at sort of broad scale impacts in a given location. So there's two ways you can do that using this tool. One way is to see when the threshold was exceeded in the past. So, and I'll show you this on the tool, but there's an area where you can look at observations of water level in the past. That's these blue lines. You see it's hourly data, so it looks like a lot of data in one place. But these are water level variations every hour. And then that's in blue. And then if you set a threshold, and you can set different thresholds, and I'll show you how to do that. But if you set a threshold of, say, 0.6 meters above average high tide, so average high tide is this dashed line here, historically average high tide. And then if you set a threshold of 0.6 meters above that, these orange circles are all the daily maximum water levels that fall above that. So you can see this hasn't happened very often. And so that may be something that's relevant for you. Say, well, I kind of know what happens at the very highest water levels these days. Let's set something that only happens pretty rarely currently. So then I can see what that extent might look like and then look at it into the future and see how much it might happen in the future. So here on the bottom, what you'll see in the mapping tool, in the mapping portion of the tool, you'll see that the flooding extents, this is what is mapped onto this threshold. So you choose the threshold, the 0.6 meters, you can see it appears here in the map in the legend. And the purple areas, so you can see here along the reef edge and on the beach over here, these are areas that are vulnerable to oceanic flooding. So not a lot of area vulnerable to oceanic flooding at 0.6 meters above mean high water. But you can see there are wide swaths of areas, including under this blue is the runway for the airport here in Tuvalu that is vulnerable to groundwater flooding at this level. And so it's important to delineate, yes, that's a little more uncertain, but this is something that the people in Tuvalu need to be very concerned about going forward, is this low-lying area where their runway is for their airport, and trying to figure out, okay, what's going to happen with the groundwater in this area going forward, and how do we address that issue? So that's one way. So you can kind of play with the threshold in the tool to look at how the frequency of that flooding has occurred in the past, and also the map of how that flooding will look like in terms of its extent and how it maps onto vulnerability to oceanic and groundwater flooding separately. Okay, so now that you've chosen a location, you've chosen a flooding threshold, the next thing you need to do is kind of think back to the stuff that Bob was talking about and think about what sea level rise scenario you want to do. And so there's another area in this tool, and I'll show you how this all kind of strings together. where you can choose the sea level rise scenario that you want to use to project. So Bob already discussed these, and here we've framed these scenarios in terms of end of century warming. So you can choose the amount of global warming by the end of the 21st century. And when you do that, what you'll see is, so I've selected 3 degrees Celsius by the end of the century. That's the green line. You'll see that the line gets a little thicker. And it also shows this kind of shading here in the background that shows the range of possibilities for that end of century warming in terms of sea level. So here we have sea level rise, the amount of sea level rise here on the y-axis, and time on the x-axis. So you can see there's a range of possibilities of sea level rise at any given time for that 3 degrees Celsius end of the century warming scenario. So you can select that here in the tool. Now, the way we communicate this is I think, effective, but also it's a little tricky because we want to try to describe in the tool that there is a range of possibilities, and this sometimes can be a little tricky to communicate and also implement from a decision maker sort of standpoint. We know that sea level is going to rise. We may even be able to say we think the most likely amount is going to rise, uh, how much that might be. But when that might occur can occur at different times depending on sort of the internal variations in the model, some of the more random things that are going on in the climate system, even though we know overall things are rising. So here we try to incorporate that by thinking about this green shading. So you've selected this 3 degrees Celsius by end of the century, but then there's this range of time for which that amount of sea level rise could occur. So here, let's just pick on around 45 centimeters. So if you have 45 centimeters of sea level rise, when might that occur? Well, you can kind of think about, well, maybe something around this green shading starts around 2065 and it ends around 2090. So that's a pretty wide range. So anywhere between 2065 and 2090 would be a reasonable amount of time to expect 45 centimeters of sea level rise for 3 degrees C end of century warming. Right. So that's kind of how we're interpreting this range of possibilities in the sea level rise. So then the last thing you can do here, and this is sort of the aha of this tool, which is to look at the actual flooding days per year going forward. Okay, so you've selected a location. We selected Tuvalu. You've selected a threshold, which we selected to be 0.6 meters or 60 centimeters above the average high tide. That's what this, I don't think I mentioned this earlier. That's with the MHHW. That's mean higher high water, but it's essentially just the average high tide. So you've selected location, threshold, and you've also selected a scenario, which we've just selected to be the 3 degrees C by end of the century. And then you get a graph that looks like this. So what we have is flooding days per year on the y-axis. So you can see it goes from anywhere from 0 days per year to all the way to 365 days per year, way up here at the top if you wanted to scroll up that high. And you've got a range, and you've got amounts of sea level rise. And you've got a range of years by which that could occur. And that's what I was just talking about in that last slide with that shading, the range of years, right? Okay, so for this threshold of 0.6 meters per year, we expect somewhere in this range of 2022 to 2037. It's pretty recent, so kind of the now sort of time frame. You may have 10 centimeters of sea level rise overall, and that would lead to something like a handful of days per year for that would look about like this. But of course, as you go further in time and the amount of sea level rise increases here, so let's go out here to like half a meter of sea level rise. Now this time frame is much later, something like 2000, like the 2060s to the end of the century. But then by the time you get there, and then you have something like more than 100 to 150 sort of days per year that looks like this. And if indeed the runway is that vulnerable to groundwater flooding, that's a real problem where your runway is essentially covered every other day for this amount of sea level rise by the end of the century. So clearly something has to change. And then you have any other amounts of flooding frequencies here in between. Okay, so I'm quickly running towards the end of my time here. So I'm going to flip over quickly to the tool itself, and I'll just run quickly through what we really already discussed here, but just so you can see it live, I think it will help just in terms of navigating the tool. Okay, so I popped over here to the tool. This is the landing page you'll see when you first arrive. It may take it a second to load, just be patient. But I'm just going to click Get Started. And then I'm going to select Tuvalu for my location. So here it is over here in the Western Pacific. And it will automatically zoom in, and you can kind of zoom in here, zoom out. You can see it's an atoll, so it's a very thin strip of land around an ancient volcano. And this is the coral reef that has kind of kept up with the water level over time. And you can see this community here on this very thin, narrow stretch of land here, which is where most of the people live in Tuvalu. So like I said before, there's an area here, observe flooding. It's clearly labeled here at the top, where you can go and see the flooding threshold. This is the water level data. You can select your flooding threshold here. There's a variety of options from 0 to 2 meters above average high tide, or that MHHW, mean high water. So you can choose different thresholds there. And you'll see that as you choose different thresholds, then the amount of flooding will change, right? And so when we get to 0.8 meters, now the runway is not just vulnerable to groundwater flooding, it's vulnerable to oceanic flooding. So you can kind of see how the map changes as you choose different thresholds. Okay, so back to 0.7 meters, then you go back to groundwater flooding. So let's actually just keep it, just for the sake of an example here, a different example. Let's put it on 0.8 meters so we know that's where the oceanic flooding is relevant. Like I said when I was describing this, so clearly here, there's the threshold. It's never been exceeded currently. We can choose a sea level rise scenario. Like I mentioned before, this is what Bob was talking about, and you can choose different scenarios here. There's another switch up here to use different amounts of warming. Let's choose a different warming level. Let's go something a little more aggressive. Let's say, what if there was 5 degrees C by the end of the century? Okay, so we have a more accelerated timeline here. We can then look at those flooding frequencies, and we can see that, okay, so we might get 0.5 meters of sea level rise sometime in the 2060s and 2080s, at which point this runway area in Tuvalu will be exposed to, anywhere from 20 to 60 days per year of flooding here in Tuvalu over the runway. So this is the kind of workflow that you can do with this tool. There is an about section here that kind of essentially outlines much of what I outlined for you in the talk, where it kind of steps through everything. And so if you need a reminder about how everything works and what order to do things and how the workflow kind of goes, you can find that here. And there's also some information here about the background, like why we care about this, what affects the results, and then some basic information about how these results were calculated. Okay, so I'm going to stop here, and I'll let you know that we do have a link here in the slides for you to go back and find the tool if you would like to see it. Like I just mentioned, we do have the instructions here for how to use it, and that does include the background and methodology if you're interested. But thank you so much for your attention. I really appreciate you participating in this training, and hopefully this was helpful for you. And now I'm going to turn it over to Denis to wrap us up.
Thanks very much, Phil. This is Denis Felikson again, research scientist at NASA's Goddard Space Flight Center. I just wanted to show a couple of slides to kind of put a bookend on the training and walk through how our current training on NASA's suite of tools on sea level change information connects to other existing ARSET trainings. So I'll provide just a few slides on this with links to those other trainings. And there are a few ways that we connect this training to the other ones. Other ARSET trainings offer either introductory or background material that can support or provide more context about the material that we talked about here. There are some trainings that make direct use of the tools that we demoed within our training as part of a broader suite of analyses. And then there are yet other trainings that provide other related applications that don't make direct use of the tools, but are very complementary to the information that we talked about in this training here. So you can find all of these trainings and many more on NASA's Applied Sciences website. All right, here are just two introductory and background trainings that you may be already familiar with, but could provide more context for the material that you heard in our training. One is the Intro to NASA Resources for Climate Change Applications. That particular training provides a broad overview of resources for monitoring climate change and its impacts. It discusses how Earth observations play a role in the assessment of climate change. And then it also provides an overview of how NASA climate models that can be used for emissions policy, assessing impacts and risk, as well as resilience applications. The second training on the slide is titled Selecting Climate Change Projection Sets for Mitigation, Adaptation, and Risk Management Applications. This training goes into much more in depth into how emissions and warming scenarios can be selected for your particular application. So it will talk about how to interpret those scenarios and how to appropriately use them for your specific applications, including how to distinguish the characteristics of the different projection sets, as well as highlighting the main benefits and drawbacks of the different types of projections that we talked about today. All right, here are two trainings that make direct use of some of the tools that we talked about for hazard and risk assessment. So the first one is satellite observations for analyzing natural hazards on small island nations. This is a previous training that looked at some of the Pacific Island nations that Phil talked about in the previous part, and actually used the NASA tool to do case studies on storm impacts, sea level rise, as well as landslides, which other tools provide on these small island nations. The second training is called Building Climate Risk Assessments from Local Vulnerability and Exposure. This training provides an overview of climate risk assessment approaches. It talks about how to utilize climate observations and projection sets. Again, how to suitably select those for specific applications in terms of vulnerability and risk exposure. And it actually steps through examples from NASA's Climate Adaptation Science Investigators, or CASI program, that is looking at preparing NASA facilities for future climate resilience. And again, it makes direct use of some of the NASA sea level change tools to project exposure of NASA's facilities in the future to sea level change. Finally, here are a couple of trainings that show related applications that don't make direct use of the sea level change tools we talked about, but are very related. The first is SAR for detecting and monitoring floods, sea ice, and subsidence from groundwater extraction. SAR is synthetic aperture radar, and this is a particular observational technique that we use on satellites. So this training builds on other previous trainings that make use of SAR data and provides focuses on two new focus areas. One is measuring subsidence due to groundwater extraction, and the other is using SAR to detect and monitor sea ice. So the subsidence due to groundwater extraction is very related because that's, in certain coastal areas, a very important driver of vertical land motion at the coast. The second training that we have here is the application of Earth observations for assessing waterborne disease risk. This training has a particular use case in coastal regions and talks about how to monitor water quality using satellite observations in coastal regions. Again, this is very related because sea level rise can exacerbate and make water quality poorer in coastal regions and exacerbate this impact. So although it doesn't make direct use of sea level projections, monitoring coastal water quality is very critical in certain places. And so this can be a complementary training to bring in another piece of information for future sea level projections. So there are many other there are many other trainings provided through ARSET with coastal applications, and I encourage you to take a look through all their trainings to see what else might be of interest to you. So thank you very much, and with that, I'll turn it back over to Sean for a summary.
Thank you, Dennis, Phil, and Bob for the wonderful presentations and demonstrations. The following summarize the concepts covered in both parts of the webinar series. Greenhouse gases added to air by human activities are warming the planet. Ocean expands as it warms. Ice sheets and glaciers melt, adding water to oceans. And global sea level rises. NASA has unique capabilities in remote sensing and modeling for assessing sea level change. Some examples include radar altimetry from Sentinel-6 Michael Freilich, laser altimetry from ISAT-2 mission, and gravimetry from the GRACE and GRACE follow-on missions. In Part 1, you were provided an overview and demonstration of the Sea Level Explorer, which provides high-level synthesis of past, present, and future sea level rise and impacts for coastal locations around the world. In Part 2, you were provided an overview and demonstration of the Sea Level Projection Tool. A key driver of the range of possible futures is the range of possible human emissions. The more we limit our emissions, the more time we have to adapt to sea level rise. Today, you were also provided an overview and demonstration of the Pacific Islands Flooding Analysis Tool to assess amounts of sea level rise expected for various amounts of end-of-century global warming, and view maps showing the extent of future high tide flooding for select locations. Before we transition to the Q&A session, I want to remind you there will be one homework assignment which you will be able to access from the training page starting today, June 17th. Answers must be submitted by Google Form with a due date of July 1st. To receive a certificate of completion, you must attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after the completion of the course. We want to thank once again Dr. Kopp from Rutgers University, Dr. Thompson from the University of Hawaii Manoa, Dr. Felikson from NASA's Goddard Space Flight Center, and Dr. Hamilton from NASA's Jet Propulsion Laboratory for their contributions to today's training. Below is the contact information for Dr. Kopp, Dr. Thompson, and Dr. Felikson, along with links to the ARSET website and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings and follow us on social media for other relevant announcements pertaining to NASA's Earth sciences. Below are a list of resources relevant to the material covered in Part 2 of the training. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order that they were received. We will post the question and answer document to the training webpage once we've finished answering and editing all questions. And we want to thank everybody that has submitted a question so far. There's still roughly 27 minutes, so there's still time. If you have a question, please do ask it. Jumping right into question number 1, what do you recommend in terms of the Dead Sea in Jordan? I use changes in surface area of the water body using satellite images. And I guess the best way to answer this is because this training was focused on sea level change and the Dead Sea is not connected to the ocean, we would not expect sea level rise to matter for the Dead Sea. More important would be the balance between evaporation and precipitation and runoff. But for that person that is interested in measuring and assessing different water extents and heights of the Dead Sea, we do refer you to 2 previous ARSET trainings, one that took place this year that was focused on NASA's Surface Water and Ocean Topography mission. And we have a link for that in this Q&A document. And we also have another training which is just as relevant to this person's question as well. That is the mapping and monitoring lakes and reservoirs with satellite observation. So whoever is asking this question for the Dead Sea, please do refer to those trainings and they should be able to guide you in your research. So question number 2, I want to know how to check sea level at a point location worldwide. So whoever answered that, if you could please unmute.
I can jump in. This is Denis Felikson. Thanks for that question. So the IPCC AR6 projection tool that we demoed in this training can be used to check, to pull down sea level projections at any location worldwide. And it comes from a gridded global data set. So you can click on any location on Earth on the map, and it will pull up the projections for that particular location. It also highlights tide gauge locations. So you can click on the blue dots, which represent the tide gauges, and get the projections at exactly the location of the tide gauge. The tool does not let you input specific latitude, longitude coordinates. So if you have a specific location in mind that's not at a tide gauge and you want this projection at exactly that latitude, longitude, what you need to do is download the underlying gridded global data set and then programmatically interpolate the projections to your location of interest. So we've put in a link into the Q&A document that points to that underlying data set, and that's what you can use to access the projections at specific latitude, longitude locations.
Okay, Denis, thanks so much. Question number 3. You mentioned that your post-6th assessment report work showed that 1.5 meters in the year 2100 cannot be ruled out. Does this mean that 2 meters in 2100 can now be ruled out?
Yep, and I'm happy to answer this one as well, although Phil Thompson and I kind of tag teamed this one. So no, 2 meters in 2100 can't be completely ruled out. And you can actually see this by looking in the IPCC AR6 projection tool at the global mean sea level data. Under a very high emission scenario, so that's that SSP 5-8.5 scenario, 2 meters of global sea level rise is still within the 5th to 95th percentile range. So although that means that it's not likely, it can't be completely ruled out.
I'll just add there, Denis, that also it's only for the SSP 5.8.5 with low confidence processes. So it really is kind of out there on the tail of what we expect, but certainly not completely ruled out, like Denis said.
Great, thank you, Phil and Denis. Question number 4. What key differences or updates regarding sea level rise projections and the understanding of ice sheet dynamics have emerged since previous IPCC assessment reports?
Sorry, I was just trying to type and think at the same time. What key differences or updates regarding sea level rise have emerged since the previous IPCC assessment report? This is a great question. I may have to take this offline and think about my answer so that I give a thorough one. Of course, and the reason I'm kind of scratching my head on this is because we are right now in the process of doing setting up the ice sheet simulations for the next, that would feed into the next IPCC report, so AR7. And so we're kind of in the middle of answering this question for ourselves under the ice sheet model intercomparison project, that's ISMIP. That's the kind of international community effort that puts together ice sheet model projections that then feed into the IPCC assessment reports. So rather than give a haphazard answer off the top of my head, I can type in a few maybe bullet points about this, but maybe I'll just offer a very general answer, which is that the ice sheet models themselves have advanced, and so more ice sheet models now simulate more of the processes that we think are important for simulating the future. Specifically, if you really want to get into the nitty-gritty of ice sheet modeling, the interactions at the ocean, the ice ocean margin, are something that a lot more models are now capable of simulating. So that's a big advancement that we are hoping to take advantage of, and hopefully the models will be able to better capture how the ocean will impact the ice sheet in the future. But I'll put in some more bullet points into the Q&A following this discussion.
Great. Denis, thank you so much. Question number 5. The data that is being presented regarding sea level rise under different scenarios, can this data be applied at a local scale, for example, to analyze a small area? And is it appropriate to use these values as input for building a predictive model at that scale?
Yeah, this is Phil Thompson. I'll take that one. And the answer is yes. This information can absolutely be applied at local to regional scales. And it's certainly appropriate to use that as input for potentially like a higher resolution or a more locally focused model that might include processes that aren't included in the more global climate models, such as waves or storm surge. And these projections that were shown in the sea level rise projection tool do include the local impact of ocean warming and ice melt. And the only caveat here is that, as Denis actually mentioned in a previous answer to a question, you can't just pick a lat long value and go anywhere. In this current tool, it's restricted to the locations of historical observations at tide gauges. So to the extent that those locations are relevant for your work, then yes, you can use them at the local scale.
Great, thank you, Phil. Question number 6. Beyond the presented total rise and rates, does the underlying sea level projection tool or its associated documentation offer data on extreme sea level events, example given storm surge statistics, tidal ranges, that are essential for dynamic flood modeling?
So this is Phil Thompson again. No, the sea level projection tool itself, it's really focused on projections of mean sea level only. It's really, you heard Bob talk about the facts framework and all those different pieces that went in there in terms of ice melt, ocean warming, and the feedbacks between these different pieces of the puzzle. So there aren't extreme statistics, storm surge statistics in that particular tool. However, in the flooding analysis tool that I described, while it's not quite the same thing as doing like a 100-year return event or a 10-year return event, it does incorporate changes in tidal ranges into those projections of high tide flooding. It also includes, and when you see those uncertainty ranges on the number of flooding days per year, it includes things like natural climate fluctuations like El Nino and others that you might have heard of. So what you could do, so on the one of the tabs there, the observed flooding tab, there is a list on the right-hand side of sort of the 100-year return value and things like that. And you could set a threshold close to those, and then you could then see how those types of events would evolve going forward. But no, neither of these tools specifically do extreme storm surge statistics, if that's what you're after there.
Great, thanks, Phil. Question 7, is there a connection between sea level rise and groundwater flooding? If so, how does sea level rise influence or contribute to increased groundwater flooding?
So yeah, so as sea level rises, I wish I kind of had a diagram or something I could point to here, but if sea level rises, as the water level rises, then that increases the water pressure beneath the surface. And so that pressure then pushes on the groundwater and actually causes the groundwater to rise vertically towards the surface as well. So on a long time scale, if you're thinking like months to years, then yeah, so as the sea level rises, it's going to push up the groundwater a similar amount. And then on a short time scales like the time scale of like a high tide, that's a little trickier to answer, because then you have to think about how quickly how porous the land material is, how quickly can that tidal fluctuation actually move in and out of the porous land surface there. So there is some trickiness on the short time scale, but for the long time scale, essentially as sea level rises, you expect the groundwater to go up a similar amount.
Great, thanks, Phil. Question 8. I used GRUN for flood monitoring in Jordan in cubic meters per second. Can I merge the results with flooding days here, or is it just about the ocean?
So I didn't realize my answers here were going to get directly shown on screen, so I apologize. I'm actually not familiar with GRUN. However, I can look into it, I guess. I'm not sure exactly what you would use out of these tools other than using them as sort of boundary conditions or initial conditions for your model. You could show, yeah, you could use the height, either the high tide flooding height or the change in mean sea level itself as sort of an initial condition for your modeling runs, potentially.
Perfect. Thanks, Phil. Question 9. Is sea level rise a contributing factor to coastal erosion? Rock barriers are used to stop sea waves and reduce coastal erosion, but will they also lower the flooding threshold?
So sea level rise absolutely contributes to coastal erosion. That's very well documented. It can be a little tricky to quantify that on the very local level, though, because if you have bad erosion in one place, what often happens is that sand doesn't just disappear into the ocean. It actually gets moved around to somewhere else down the beach or to a different barrier island or something. So as you lose sand in one place, it largely accumulates in another place, and so it's a little tricky on the local level to decide how much of that erosion is due to sea level rise. But if you zoom out enough and you see that over a large enough area, then yes, on the whole, sea level rise does contribute to increased erosion. And then on the question of adding barriers to stop waves and reduce erosion, generally what that does is it raises the threshold. So as you build the hard infrastructure at the coast up, that raises the threshold for flooding, meaning that you need to have more sea level rise and or higher water levels to create flooding conditions.
Great. Thanks, Phil. Question 10. Is the tool only for the Pacific region? Can it also be used for other parts of the world?
Unfortunately, right now, the tool is only available for the Pacific region. However, we do have plans to expand that globally, again, to the locations of tide gauges where we have data, expand that globally over the next year or two as either the processing for the tide gauge data is completed or as we have processing for the digital surface maps. So we need to have digital surface maps of the elevation in order to do the flooding extents. And so those are also being processed as well by the NASA sea level change team. And so as those two components become available over the next year or two, we'll expand it out globally.
Great, thanks, Phil. Question 11. Is there any published scientific papers or research accessible through this tool's documentation that detail the methodologies, data inputs beyond global mean sea level, and validation of its projections for chronic or extreme flooding events, similar to the future flooding frequency assessment shown in the previous slide?
So this is Denis again. I'm happy to jump in and say in general, yes, there are peer-reviewed papers that back all of the tools that we have shown in both parts of this training. And those papers detail the methods and the data that underlie all of the tools. And I'll be happy to provide links to those things, to the papers specifically after we finish up the training.
Awesome. Thanks, Denis. Question number 12. How frequently are these tools updated as sea level rise projections improve/increase?
Well, as both Bob and I, this is Phil Thompson again, as both Bob and I talked about, these tools are based on the IPCC projections. And so those projections get updated in an official capacity as the IPCC reports come out. And so we expect to update these tools as those IPCC projections update, as the reports update. And so that would be something like a 6 to 7 year update cycle.
Great. Thanks, Phil. Question 13. Is there a simulator website available to see what happens worldwide or for a region if the sea level changes up or down?
So, well, Phil unmuted as well. So Phil, feel free to correct or add, but I'm not sure exactly what's meant by simulator in this case, but I would say that the combination of the tools we presented will give kind of the full picture of what will happen worldwide. But maybe I'll see what Phil has to say about this.
Well, my answer, Dennis, is going to be similar to yours. I think that's generally correct. I think you can see for a given location where we have actually both of these tools available, you can kind of get the sense of what happens. However, I'm wondering if the spirit of the question isn't more about sort of a larger scale visualization of, so sea level goes up in a place, and can you see a large swath of land being impacted or flooded? I think there are some other tools on the Sea Level Change Team website at sealevel.nasa.gov. So you might check that out. There are some other tools there that can be that do have some of that capability. However, those larger tools, though, like that, it's a little hard to see fine scale changes at the coastline. So some of the things that we're seeing, they're pretty subtle in terms of like their spatial extent. And so large scale pulled back maps of what happens with sea level rise aren't always that effective. And that's one reason why we focus here more on individual locations, because then you can really start to see how those fine scale impacts emerge and how the extent of those impacts changes.
Well, Phil and Dennis, we want to thank you so much, one, for excellent presentations, and as well as just excellent job answering these questions and answering all these terrific questions that the participants submitted. I want to remind all the participants that if you are interested in receiving a certificate of completion, the homework is accessible from the training webpage. So please do, you have roughly 2 weeks until July 1st to complete those homework via Google form and submit your answers to receive credit. And also, I also want to remind the participants, there will be a survey going out to you this week or early next week. And we greatly value the feedback that we get from that survey. That's how we are able to, plan for future trainings and also improve the trainings that we currently give and provide. So please do take the time. It takes 5 to 10 minutes. Hopefully it does not take too much of your time, but we greatly value that feedback. So please do, when you receive that in your inbox, please do take the time to fill that out. So Dr. Felikson and Dr. Thompson, as we're wrapping up this final part of this 2-part webinar series, and we're, kind of winding things down until the next training, I wanted to ask you if you had, or just reflect on anything that you wanted to provide in terms of, thoughts or comments to the participants that were joining from all over the world, really. And maybe Dr. Felikson, we could start with you and then move to Dr. Thompson. Thanks.
Sure. Well, I'll just say a big thank you to all of the attendees for your interest and your excellent questions during this part of the training session. Also, big thanks to Dr. Bob Kopp and Dr. Phil Thompson for contributing this. I thought these were an excellent set of trainings. Thanks to the ARSET team. And these questions are really helpful, and we really appreciate it, because personally, it's making me think more about how we can improve on some of these tools and offer some more functionality that people might find useful. So really appreciate everyone's interest and feedback. And yeah, thanks.
Yeah, I'll just echo what Dennis said there. I think I just also offer my thanks to the whole ARSET team for putting this together. I think it worked out really well. I think all of your attention and interest in this topic really highlights the importance of this information and how many people want it and need it, and that it's really essential that we continue to do this work. So thank you very much for all the attendees out there. Having close to 250 attendees is really awesome for this, and I think it's something that we can take away and that NASA can take away to demonstrate the importance of funding these types of projects, and also really going through the whole suite of analyses, and then tool development, and then education for those tools, putting all those things and stringing them together is really, really awesome. And not a lot of agencies do that. So I thank NASA for doing that. And hopefully we can continue to do things like this in the future.
Wonderful. And so once again, we want to give everybody Dr. Bob Kopp, Dr. Denis Felikson, Dr. Phil Thompson, and also Dr. Ben Hamilton for contributing to part 2 of today's training. I also want to thank the ARSET team, Natasha Johnson-Griffin, Selwyn Hudson-Odoi, and Jonathan O'Brien. Thank you for working in the background to make this training a success. And most importantly, we want to thank all the participants. Thank you for your time today, for your interest, and also for submitting such terrific questions. So we look forward to seeing you all at an upcoming ARSET training. Be well.